All right. It is officially time to assign homework 5 Tuesday. So welcome on in. Your day's been going well so far. So let's go process off itinerary. So just a quick rundown through our syllabus. Here are the test topics left to cover. So today we'll go over input buffering, and I'll go ahead and start threading and race conditions. Maybe we'll finish this today, maybe we won't. We'll see. And then tomorrow we'll probably talk about threading again and interrupts. And then we'll go ahead and maybe explore a little bit of assignment 5. Then you should have your test on Friday. So I'll probably assign you a quiz on Wednesday that might cover these 3 topics that we're going over today. And then Thursday, I don't plan to teach anything new. So I'll probably just give you the day on Thursday to start working your assignment and study some of the materials. I plan to make the test the same times that you took it last time. And on Monday, we don't officially have class because for some reason, July 5th is considered Independence Day weekend, so I guess there's no class that day. But that's okay. We should have enough time to cover all the materials on the itinerary or on the syllabus. Maybe I'll give you homework 6, depending on whether or not I want to really do anything with these topics, and then maybe a MIPS assignment as well. Okay, so that's our tentative itinerary for today and the rest of the week. And go ahead and start on the lecture topic, and then maybe we'll go ahead and talk about our homework assignment that's due this weekend. So today should be a relatively short lecture, hopefully, so we can talk about the homework a little bit more. All right. Remember when we're in the von Neumann architecture, right? So if here's your CPU, where the CPU has all the registers, here's the bus. So the bus are the interconnectors, the thing that connects all of our components together, and that's how they're able to send each other data and interact with one another. So here's your I/O, and then your secondary storage. Okay. Of course, this is the bus. All right. So hopefully this diagram is familiar to you by now, because I think I've gone over this at least twice a week. Okay. So whenever you execute a program, the loader will load the program into the memory. Right? So here's your and any files that you need to read, let's say they're stored in secondary storage, your program will have to ask the OS to read the file. So say that you need to get data and send from secondary to RAM, right? Okay. So every time you ask your OS to read something from a file, this causes some overhead, right? And you'll talk a little bit more about the OS and the overheads and some of the other topics we'll address today more in detail when you do get into OS. So this is more of an introductory kind of overview of some of the things that your OS does. So when we're asking it to do a sysread, obviously a system call invokes the OS, and so OS has to go to that file and read it. Okay. And so it'll pause whatever it's doing, and then grab the contents and then give it to your program, and then somewhere along the line you'll resume the program, and that causes the overhead. Okay. And same thing, right? Information that needs to be obtained goes to the bus and goes to wherever it needs to go, in this case RAM, right? So the bus also causes overhead as well, right? The bus is like what we call a bottleneck, or what we call this more specifically bus contention. So essentially, if more than one process or program or anything causes the usage of the bus, we have to pause whatever is taking place to perform those other tasks. And the CPU, once you get into OS, you'll learn about the different scheduling algorithms and structures that your computer does in order to kind of prioritize which operations utilize the bus, memory, and so on and so forth, CPU time, later on. But just know that in this architecture, that there are some major bottlenecks that slow down how fast your program will run because of all these system calls, the OS invocations, the passage of data, and like the channel that it gets passed through, or the bus, can always be contended for with different processes. Because obviously, so like right now, I have a Photoshop process, right? I have a program for Photoshop. I might have one for streaming. Maybe you have a web browser on. So those are all different programs that get prioritized differently depending on what your OS thinks is important. Okay, so how does this kind of tie into buffer input or input buffering? So let's say, for example, your program has 1,000 lines, or maybe let's make it more exaggerated. Maybe you have 1,000,000 lines of input to read, right? So maybe 1,000,000 lines input. Obviously, each line can contain upwards of a few thousand characters. So you have relatively large input to put into your program, right? So if we were to read this one character at a time, right, that's at least 1,000 lines times how many characters those lines are of input and invocations to your OS. Remember, in the earlier examples, we were prompting the user for input one character at a time. Obviously, user input probably wouldn't be that large, so the OS overhead wouldn't be that substantial. But if we're reading from a file, that's a little bit different, right? Because the file is not necessarily going to change, assuming you're doing a read-only operation, right? So reading that file one character at a time now creates a huge amount of overhead, especially for larger files, right? So if we were to read, let's say each line maybe had 1,000 characters, right? This would be roughly, what is this now? 1 million. So it'd be like 10 billion characters, or 10 billion invocations or syscalls that your OS has to do, and that becomes a huge bottleneck. So instead, huge OS overhead if we invoke syscall. For 1,000 characters. Okay. So instead, what we can do is do something called input buffering. Where we can essentially read a chunk of data into a large array or buffer. It's the buffering part. Basically, if we were to read each line, so in this case we'd have 1 million lines, right? Then in this case, right, we'd only be invoking the OS 1 million times, right? Versus 10 billion, right? So that's one way. So basically, when we say if we limit the amount of syscalls, it should inherently imply that the process is faster. But we read essentially the same amount of data. Right? We kind of brushed up about how reading too much data at a time can lead to bad things with the stack buffer overflow, and how that could be a security vulnerability. But when it comes to a file, you can essentially expect where you can test for where the end of the input is. So if you do a few checks here and there, then you should be relatively safe from that. And that's also if you're invoking using the stack. Okay, so something that you might be familiar with is maybe the get line function in C or C++. And in higher level languages, obviously this feature is it hides the complexity of what you have to do, but that's not the case in assembly. So we'll probably not end up coding all of this, but I may just give you the algorithm. So if you want to convert that, then that's perfectly fine. But of course, we will never really need to read in that much lines of data for your homework assignments. So this is just more of a concept that you should be aware of, but not necessarily going to use in this class. Okay, so we have the getLine function, and we know that this is a line feed terminated operation. So remember, if we have a data file, right? Let's say 0, 0, 0, 4, whatever, 2, and then we get a line feed, even though you can't see it, it will tell us to start a new line. Maybe you have some more data here, some more data here, and each one of these is terminated by a line feed. So you know when to stop and grab the next line. And then when there's no more input, we know that while it's not written, we know that it's the end of file when there's no more input. Say example data.text or something. Right? So we know the getLine function is line feed terminated, and it usually returns a status, basically saying whether or not there's any more data to be read after this. So it generally asks, so probably looks something like this: status equals get line fd. So text line and max. So something like this. So basically, you have your file. You're getting it from the buffer you're putting in. So this is file descriptor. This is the buffer, and then this is the size of the buffer. Yeah. And then it returns true if the line is available. Okay. So in your textbook, it does have kind of a nice little algorithm that we kind of go through just to see things we have to convert to assembly. But we won't be doing that in this class. But it might be good to know at least what the algorithm looks like. So if you want to reference this, this is also on page 253 of your textbook, or PDF page would be 267. So if you want to follow along in your book, that's also fine. But essentially, it looks something like this. So if you have a line get line, you have your FD, your buffer. So in this case, we called it text line, and the max length of the buffer. Okay, so I'll just write it in terms of pseudocode. So it's probably do while. Basically, want to keep doing this. You basically test whether the current index, so how far you are in the line, is greater than or equal to the max length of the buffer. And then you can read to buffer. So just store the characters in there. So there's a few things that can happen, right? You can get an error, so you can obviously do an error message. Error, do something. So you can either print out the message and then terminate, or if it's fine, then what we can do is just reset the pointer. So now you're going to point to the next line to read, and if, and then you can test whether it's end of file. So basically, if the number of characters you read is less than the buffer, number of characters read twice, so requested, then you know you're at the end of file. So EOF is true, and if EOF is true, then you can leave, right? Because there's nothing else to read. And that's more or less it. Some other stuff, but that's essentially input buffering. You don't really need to know too much about it, but just know it's a method to reduce the overhead for your inputs. Okay, when you're reading from file. Okay, so that was input buffering. Hopefully, there's no major questions on that. We will maybe have a question or two, very, very simple about input buffering, but nothing too crazy. Okay, so let's go on and move to parallel processing. Okay, so when it comes to parallel processing, there's two different types of parallel processing. So the first type is the distributed type. Okay, so distributed type essentially is when we utilize multiple machines or computers, and they do all the work. They split the workload, and they do something like this. So maybe you have machine 1 here, machine 2 here, and machine 3 here, and they split the workload, and they basically are feeding the information to maybe the machine 4, so that they can join all the work that they're done. So some words you might hear regarding distributed processing is maybe something called a cluster, right? So a cluster usually involves a bunch of localized machines, so in the same room or server. That way, the communication bottleneck is reduced, right? So if the distance between talking to machine 1 and machine 4 is shortened, then it reduces the communication bottleneck. By reducing travel distance. So an example of a distributed type of computing, you might have heard of something like Hadoop for big data, right? So obviously, if your data sets are extremely large, let's say if you're working with Facebook data or Google data, though that tends to be relatively large for one machine to handle. So what they do is they employ some sort of parallel processing or distributed processing, where they break down different parts for different machines, and they usually have a bunch of clusters of these machines so that they can work. And of course, we can expand this architecture even further, right? Have multiple clusters being controlled by another, say, machine 7 in this case, and then so on and so forth. So we can expand this kind of architecture outwards like that. And sometimes these machines can also talk to one another instead of just talking to a superior machine that manages their processes. So maybe you have 3 or 4 machines that are talking to each other, and then maybe 4 here. You might hear a term what's called a hypercube. So if each of these machines, let's say in this case, they can connect to 3 other machines, then information can be spread and used in those relative locations. Okay, so you might hear the term hypercube. Not too important because in this class we're not really going to be talking a lot about distributed processing. Okay, but it's still good to know that that's one type of parallel processing technique. The second one is the one that we're mostly concerned about, and that is the multi-core processing, or in other words, it's a nice looking picture. Yeah. In other words, this is what inside your chip does. So inside your CPU, right, you have these little threads, depending on what your CPU architecture is. But let's say you have RAM here. So let's say here we have some kind of shared variable, right? And this thread right here can set the variable, while simultaneously a thread can also go into the same memory access and read from that variable. We'll go into more details on this kind of thing, but essentially your CPU can run multiple different processes in parallel, well, in quote unquote parallel. So here, this is called multi-core threading. So you either use your cores or what they call threads to perform the same same or similar operations, and they can utilize the same shared memory, so variables and functions. So it's nice because it's it's remote, or it's local to the threads. Okay, so that's so maybe some other stuff we can talk about is there is a problem with the shared memory thing, and we'll talk about it a little bit. And one of the other limitations to it is the number of cores you have access to. So obviously you're limited to your architecture, whereas a distributed system like this can essentially expand outwards more. Of course, the more the more connections it has, the more bottleneck it does for this distributed approach. But for multi-core threading, your only limitation really is the amount of threads you can have. So before we go into why having shared memory can be somewhat of an issue, maybe it's time to dive a little bit into a 218 horror story time. So 218. Okay, so I did some snooping around and found a previous assignment that is roughly in this lecture area. So essentially, I don't have the image of the assignment, but I can kind of tell you just some main concepts in a nutshell. So you get an input file of palindromes. So a palindrome basically is the first however many characters, letters, or numbers must match the latter part. So if I gave you a number like 1, 2, 3, 4, 3, 2, 1, let's just cut it short like that. This would be a palindrome because you would see 1, 2, 3, 4, and then you'd see the reverse of that afterwards. Right? So 1, 2, 3, 4 going this way as well, towards the middle. Okay. So you can input file of palindrome digits, or digits that may or may not be a palindrome. And it's quite a lengthy list. So let's say, for instance, it had 3 million inputs. I don't actually have the source text, but let's just make an example so that we can kind of show parallel processing and why it's nifty. Okay. So we have 3 million inputs of digits. Whether they are or not palindromes, we don't know. So it's our job to basically split this workload into a few threads and try to increase the performance time or the execution time of the code to calculate all 3 million of these digits to see how many of them are palindromes. So, algorithmically speaking, you might think, okay, well, it's very easy to kind of split the work into 3 threads, right? You might say, I can assign the first 0 to 1 million digits to this thread, called thread 1, and maybe the next 1 million plus 1 threads or digits to the next 2 million threads. We'll assign thread 2, and then maybe we'll say 2 million plus 1 all the way to 3 million to thread 3. And they should come back with the results, and the workload is what we call evenly spread out, right? But that's technically not the case. So if we were to break this down even further, we would notice that the numbers between 0 to 1 million are relatively small, right? So we go from 0 to 0, 1, 0, 2, right? And let's say like 202 is a palindrome. And the numbers here are sub 1 million, let's say, right? And the numbers here grow larger, so there's more to check here, and there's more to check here. So maybe if we were to kind of graph this out, so let's say the first initial block of time is some overhead for setting up these threads. And then so thread 1 may take less time than thread 2 and thread 3, right? Because the numbers here are less work to calculate as opposed to the lengthier numbers here when we get to the millions. Actually probably thread 3 would have similar time to thread 2 because the amount of digits is relatively the same. But we can see that the workload is not evenly distributed, so when you join these threads and their results back, we're bottlenecked by the slowest thread. So slowest thread bottlenecks the process. Right? Because even though thread 1 is finished, thread 1 doesn't have the final result. It's the union of the 3 threads that gives us the results. Okay. One thing that we might do instead would be to maybe go ahead and initialize some sort of a because remember in their diagram we said that was the other page, but remember we said that the threads all can read the same memory, right? So whatever that shared variable is. So let's call this variable index, right? So maybe my index starts at 0 and I want it to end at 3 million. And maybe I'll assign the first 1 to 1 or 10,000 values to thread 1 to do. Then I'll assign the next 10,000 values for thread 2 to do. And I'll keep assigning them increments of 10,000. So even if thread 1 finishes early, I can assign a new batch to thread 1 to do while thread 2 and 3 are still performing their operations, right? So maybe thread 1 ends up being used multiple times, but the end result is that maybe they finish relatively similar in terms of time. So the bottleneck is reduced because we shared more indexes to thread 1 to do because it finished faster. And you might say like, okay, well, maybe this kind of model makes sense, and it's relatively fine, right? But what happens is, let's say when we update the index, right? So to model, so we know that the index will need to be incremented, right? By say 10,000 every time a thread finishes and asks for another batch, right? So remember that the threads can all access memory in parallel, right? So if my thread 1 and my thread 3 finish at the exact same time, they can read this index value at the exact same time, meaning that thread 1 potentially can read values, say 20,000 to 30,000, and thread 3 can also simultaneously read values 20,000 to 30,000 because they're accessing the value of memory at the same time. So this is, this isn't what we call necessarily a race condition yet. This is kind of the premise towards it. So this happens when both threads access same shared. So it's important that the variable is shared. Variable same time. So while reading isn't as dangerous as overwriting the value, right? So in this case, maybe we just end up doing the operation twice and wasting some processing time. But that's not as bad as, say, if instead of detecting whether it's palindrome or not, maybe we were to replace the value inside the array or inside the document with something else if it wasn't a palindrome, right? So then it would override data, and that then becomes a race condition. So a race condition see. Someone asks, would you do n plus 1 n plus 2 where n is divisible by 3? So if you're referring back to this one, or the other ones. You're referring back to this right here where we're splitting up the workload, splitting the workload evenly. You wouldn't do, well, you could do n plus 1, n plus 2, but you would be reading less input at a time, and then we would maybe encounter the extremely large input overhead buffer thing, right? So where we're calling the syscall too many times, and that causes like our process to lag a lot. So that's why we do it in batches, right? But if I were to evenly split them into 3 batches, the workload may not necessarily be the same. So what I can do is divide them into smaller batches. So in increments of say 10,000, right? If a thread finishes early, then we just give them more batches to do. So that's kind of the logic behind it. Just to catch everyone up. All right. So in this case, a race condition basically occurs. Race condition basically occurs when multiple threads, usually threads. I mean, this can happen in the distributed system as well if you're not careful. But if multiple threads simultaneously change a shared variable, it's okay to access the variable. So reading is less destructive than a writing command. So in this case, we would just perform the operation more than once. But if we were changing the value of the index per se, that will probably cause a race condition, right? And we'll go through a little bit more examples on potential race conditions. Okay. But this comes back to haunt you in 370 a lot. It's a good test question in 370. So you might ask, okay, well, how do I prevent this race condition from happening? So in this class, we won't really go over too much detail about how the OS handles everything, since you'll learn about it more in OS. But the concept essentially is we want to block other threads from accessing the shared variable. If it needs to be changed, right? So the easiest way to do it is just to simply deny access to that variable during the time that another thread is using it, right? So almost like what they do is they call a lock, right? So you want to lock your variable so that no other thread or process can change that variable, and then unlock it once you're done. So maybe we'll talk about the lock instruction, or well, technically it's a prefix, but we'll talk about the lock prefix a little bit more maybe tomorrow. But if the lock prefix basically says, if you have an instruction, say like increment RAX or something like that, right? You can call lock, right? Or increment maybe, let's say keyword index, right? Something like this. If you call lock in front of the instruction, then what happens is this, whatever this is doing, makes it so that it is atomic, meaning that um, you cannot have another thread or process touch the contents of this uh, until this process is done. So this process becomes makes next instruction atomic. So that means there's no system interrupts, no touching of the variable that's in use or any of that until the operation or the instruction is finished. And you'll learn more about interrupts probably tomorrow, but more of that in detail in 370. Shouldn't we put a lock in front of almost everything then? No. So if you're not accessing a shared variable, then there's no need to lock it, right? So you're basically asking the OS to do more work for you if you lock the variables, right? So what happens in threads are, so let's say if we have thread 1 and it's going to use a shared variable here. Now let's say thread 2 also does it, but it's somewhere there. Or how about we do a different diagram instead? Kind of like a timing diagram, right? So thread 2, maybe thread 3. Okay, so maybe at 1 millisecond, we call some function or some, let's say lock some instruction, right? Let's say lock increment keyword. What do you say? Index, right? Okay. And then at maybe like 2 milliseconds, we also called it here, right? Lock. Right. But the process isn't done until, say, here, right? So while you don't have to write code for it, let's just say release or unlock keyword when done. Or index, technically, right? Unlock index when done. Okay. So once we reach to this point, right? When we're accessing this index right here, the thread will basically halt because it's waiting until this variable is free again. So if, for instance, thread 3 wanted to do stuff, right, that didn't involve using that and it was halted, then we'll bottleneck the rest of our threads. So if we lock everything, it means that this instruction needs to finish in order for, say, the other instructions to execute. So make sure that the lock is used sparingly only for shared variables, and only if those shared variables need to be handled with care because of a potential race condition. Okay, so we can go through another example of race condition that might be a little bit more clearer. So let's say we have a simple function, and all it does is it increments some index, right? Okay. And you can do the same thing, right? Where you tell, where you call the threads to do this task. So maybe you'll have the first thread. So maybe you say wow, or maybe we'll do sum instead of index, right? Sum. So maybe you have an index, right? That starts from, say, 0, and you want to do it 10,000 times, right? So you just basically want to add 1 to a running sum 10,000 times, right? And so similar fashion, we'll split into threads to do, right? And you expect the result to be, let's just say sum at the start was 0, right? So you expect the result to be 10,000, right? Because you split up the workload to 3 different threads to add 1 to the sum. Maybe return to add 1 to the sum every time, right? It's invoked, and that kind of makes sense, right? So in this case, sum is your shared variable. Maybe here is the sum. So if thread 1 works on it, it reads sum equals 0, right? It'll say, okay, well, I'll take that and I'll call function 1, and then function 1 will increment it to 1, okay? Thread 2 might look at it and then increment it. Thread 3 might look at it and increment it. Okay, but there's nothing stopping from thread 1 and thread 3 from reading this variable at the same time, right? And running the code and then updating sum at the same time. So if sum is updated in both 1 and 3 at the same time, you only increment it to 4 and not 5, right? So a possible result for this could be 98,942 or something like that. Oh, and not 98,000, maybe 9,894. Because some along the way, if we didn't lock the variable, the shared variable that's being written to in this function, because there's no lock instruction here, what can happen is you'll end up with a different number than your expected outcome because of brace condition. Okay, so it's important that if you're using a shared memory or a shared variable, that you lock it if you're going to make changes to it. And if we have time tomorrow, I'll go into more detail about it. But this is mostly a topic that you'll experience in 370. It is a little rather difficult because there's some algorithms that we kind of have to go through, like semaphores and using mutex and stuff like that. So I'm not sure if I'll go that much into detail, since your OS class should cover that. But here's a good precursor to your OS class, and at least know that the lock instruction is how is one way that you can use in assembly to handle race conditions. Okay, so CS2 370 sound like CS218 part 2, kind of. A lot of the stuff, because we remember we're closer and closer to machine code, basically, right? Where 1-to-1 corresponds to machine code. We need to know how to talk to our machine in a good machine interface that we can kind of relate to is to the OS to do a bunch of these system instructions. So threadings and interrupts and stuff like that, they're all very closely related to each other, which is why you see some of these concepts appearing now, and then later on you'll go into a lot more detail when you get to OS. Yeah, just a precursor. Nothing too serious. Maybe on the test I'll ask you about race conditions. I think that's definitely going to be on the test. And maybe give you an example or ask you about what instruction or prefix to an instruction is called to stop the race condition. Of course, we just covered that. There's a lot of different algorithms that you can employ that utilize the lock. So some things called spin locks. Sometimes you'll hear like a BBQ. Sometimes you'll hear, those are all just different algorithms and methods to ask your OS to basically freeze. So what happens when you call a lock is that it will basically freeze the part in RAM that the variable lies, or the shared variable lies in, and then it can only be accessed by the routine that called it, or the thread that called it. Okay, so far we've been only working on single thread processes. Maybe depending on how difficult some of those algorithms are implemented, I may or may not give you your assignment 6 on threading. So we'll see about that. Okay, so hopefully today's topics weren't too difficult. They're more conceptual than actual implementation. If we have time this week, maybe I will try to do something very light on the implementation. Let's see. Okay, so any questions on parallel processing using multi-cores and threading? Not, so we can go ahead. Assignment 5, perhaps. So I was pretty nice this morning when assigned. It's not as bad anymore. So you'll get 3 files. You'll get a template as per usual. I try to put very little stuff in the template, but enough for you to work on. So maybe can pull up the template. So download the template. Well, there's two files. One is the input file, and one is the template file. The input file is relatively short. It is just 10 lines of 2-digit numbers, or 1 to 2-digit numbers, I guess. So nothing too bad there. Okay, so in this homework assignment, this is the source code, and we'll just edit the source code. Let's go ahead and look at the assignment. So there's the edited version, which is the one that I've given you. I've severely shortened the amount of code needed for this one. So I'll give you the premise, and then I'll show you maybe the horror stories that would have been your assignment had I not updated it. So assignment 5 says, is homework 5 on Canvas? Because I can't see it. It should be. It should be on both courses, I believe. So even if you are in session 2, so it might not be uploaded in session 2 for some reason. Got really quick. Yeah, so it should be there. Everything is the same. So sometimes I think WebCamp is just spaghettis and does not copy fully, but it should be up now for both classes. So you'll get the template, you get the edited version of homework 5, so make sure it says edited and not the full version, and then the input text. So you'll need to download all 3 of these. I guess you don't have to download the PDF. Let's go ahead and look at the edited version. So, or actually, let's look at the full version because the full version has more context, and then we'll go to the edited version, which is the reduced amount of work. So here's the original file. So here's the premise. So after being chased out by the bears, Goldilocks finds herself interviewing at a porch, chair, and bed consultation firm. A hiring manager has conducted a small test to see whether or not she's qualified for a job. So a manager will give her 3 questions, each question containing 3 different values for each item. So in the text file, I used to have 9 entries. And the first 3 entries represent the temperature in Fahrenheit. All you have to do is compare the temperature to see if it's greater than 190. And if it is, then output porridge is too hot. If it's below 120, you have to say that it's too cold. Otherwise, it is just right. So similarly, you'll get 3 numbers for the chair, and then you'll calculate the just the area of the chair not the surface area or the volume, so very easy. And we'll just assume that it's a square shape, so that all you have to do is multiply the side twice, so side squared or side times side. So if the area is 120 units long or large, then it'll be too big. Otherwise, it is fine. And then the last part was whether or not it had a rating of 5 or higher for the hardness. So it's not too important. The task was simply to open the file. So we'll brush up on system open, right? So don't edit the values. So the new input file is there, the correct values. So you read the file, and then because remember when we're reading things from using the system command, they're always converted to strings. So we need a way to convert that ASCII string of digits into the ASCII values. Also, to read each line, you have to terminate by the line feed. Okay. And then you have to convert the ASCII to an integer. So this is basically the opposite of what you did in assignment 4. In assignment 4, you converted into ASCII. Now you're doing the opposite. And then return the integer into RAX. So here's a quick formula on how to do it. So the integer you're looking at is equal to the current integer plus the digit. And to calculate the digit, you just subtract the value of 48. This should say ASCII with 2 i's, but alas, there's a typo. Okay, then you would write 3 functions. So evaluate porridge, evaluate chair, evaluate bed. This one takes 4 arguments because there's one extra message that says the porridge was too cold. The other 2 basically you send in whether the hardness of the bed and the 2 print messages to print out, and then you just print them to the console. So an example would have been like this. So if it was temperature was 210, then you would output the porridge is too hot or too cold or whatever. But the revised homework, since I'm so nice to you guys, all you have to do is do the middle part. So she's now only at a chair consultation firm, and you only need to do the area part, and that's it. So instead of having 70 extra jump instructions to compare your porridge temperature and your bed size or your bed hardness, all you have to do is calculate the area and then output whether it's too big or if it's just right. So I would significantly reduce the amount of work, but I changed the values to reflect the area of the chairs a little bit better. Okay, so hopefully that is not too difficult. Are there any questions? So I guess we'll look at the template. I've kind of mapped it out for you. So hopefully these are all the system services you'll need. So you have write, you have standard out for print to the console. This is for executing code. Line feed null defined for you. Open, close, and read should all be there. So hopefully that's all the system services you'll need. If you need any more for whatever reason, you can always add your own variables. The ASCII print from last assignment is close to what we do for this one. Kind of, but it's the opposite, right? Because the previous one is you will take an integer, convert to ASCII. But in this case, you're reading input this time. So you read the input as ASCII, convert the ASCII to integer to do your calculations and your checks, and then output whether the chair is too big. So I have already defined the message for you. So all you have to do is pass the address of the message to your function, and that's it. And the chair is just right. So make sure you count the amount of characters to print out. I probably forgot to do that. So if you want to define it or just hard code it in your function, it's fine. So here, this part, you'll probably do a loop to read input from file, and then probably invoke function to print whether chair is too big or not. right? Here, before that, probably invoke function to for ASCII to int and return. So something like that. So here are the functions. I've already predefined kind of the structure for you, and I was nice enough to also tell you what parameters you should be passing in. So, I mean, you can make modifications to it, but this should be more or less the skeleton for it. Okay. So hopefully not too difficult. You've already converted into ASCII, so ASCII to int is just the reverse. I'll leave you to write the code for these, but I guess while we're doing the loop, we can do something like, so we already know the value is returned to RAX, so maybe here, oh, also define a buffer for you to store your ASCII buffer. So when you read, you can fill out this buffer. You don't have to, but if you choose to, you can. So this one takes the buffer, so can you move, so maybe something like a move buffer address to RDI, so ASCII buffer with no dereferencing, and then call ASCII to int, and then we know that RAX is the value returned, right? So we invoked it, and then we need to invoke the function to print. Invoke the function to print, so move RDI RX, which is the integer. So if we look at the value, so integer value to evaluate, so RX here, address of message big, so move RSI big. That should be, oh, and then we have to call the function, call eval chair. And then your eval chair will print depending on what it is, and then you will you'll loop. Something along the lines of that. I'll leave you to fill out the rest of it. So, are there any questions on assignment 5? I need to give you more homework points. So this one is worth 120. So make sure you do this and get a good early start to doing it. Just don't expect debugging to be done in an hour unless you're really good at coding and you never make mistakes. Then you're perfectly fine. All right, so hopefully not too difficult. Should more or less be everything that we've been doing so far. I've given you the formula for converting the ASCII into the digit. All the digits are relatively small, so you should be able to figure out more or less whether or not your input and outputs are correct or not. So it shouldn't be too bad. Any chance you can reveal functions and give some pointers on using them? I mean, yeah, we can review some functions. I'm not really sure what you mean by pointers on using them. So we can go ahead and kind of tired of writing. So let's just use the use Visual Studio Code for now. If we want assembly function, right? So 6. Okay, so of course we have our section dot data section dot we have our global start. So this tells us where, tells the linker where to start our program. And then we have our our exit functions. I'm just going to copy paste this over, and maybe we'll take these as well. So functions are relatively simple. So function. Okay, so remember, functions are forward referenced, meaning that you can invoke them earlier in your program during the first pass of the assemble process. And then by the second pass, they should be all mapped out and nice for you. So remember, that's the, let's zoom in so that you can see more, I guess. Arguments 1 through 6 are stored in these corresponding registers, right? RDI, RSI, RDX, RCX, R8, R9. Okay, and then our arguments 7 plus are stored on the stack in this order. Okay. So maybe we can do, so maybe I'll do like move RDI, we'll just say argument 1, right? Of course, argument 1 will, maybe we'll do this keyword arg1. So just to make it look nicer, right? Keyword arg2, and so on and so forth, right? Up to move R9, keyword, say arg, right? So you've stored all your arguments you want to pass to the function. Maybe we have more, right? So let's say we have 2 more, right? 2 more arguments. Go stack, right? So we have 2 more, then we have to push them on a stack. So maybe I can do something like this. Arg, it's not arg3, it should be arg6. So let's say I want to push argument 8. 7. So notice I'm doing them in first order, 8 first, then 7, because 8 goes before that. And I can say push RX. So now I changed RX and I can push it again. So on my stack, all right, my stack should look something like this, right? So current stack will go left to right. So this being the top of the stack. So let's say higher memory is here. So we might have contents on the stack, and then on the stack, we just placed in R8 and R7. So when we pop, it'll be not R8, ARG8 and ARG7. So like this, and then we go all the way down, and this is maybe the heap, right? Heap, but this is the other parts of your data. Okay. So we can go ahead and call our function. Let's call it function. Let's call it F1. So F1 will basically get all these arguments that we passed in from RDI to R9, and then we can use our standard calling convention to grab the 2 off the stack. And according to my standard calling convention, after okay, since I have pushed 2 arguments on the stack, I need to update RSP by 2 times 8 bytes. Remember that each item on the stack is 8 bytes, so I need to say add RSP 16. So functions, right? So let's say this function right here. So global F1, F1, right? So let's say this function takes in 8 arguments and sums them up, or something like that, right? Then returns value back. All right. Or maybe we'll do subtracts them in order, because or if or like, in addition order doesn't matter, but in subtraction it definitely matters. That way, how the argument 7 and 8 work, we have to do them in order, so you can kind of see how that goes. Okay, so remember my first argument is an rdx, so move, let's say rex, rdi, so move first argument into rx. Okay, then we can move, or we can say sub rx with rsi, so subtract second argument. It could be something like sub rx, the next couple, right? So rdx, and then so on and so forth until we do rx r9. So we've already, by here, we have subtracted subtracted the first 6 arguments. Now we need to grab these 2 on the stack, right? So before this, actually, remember we have to do our standard calling convention. So push RBP and move our RBP SP, right? So now my stack looks like this. Stack looks something like this. When I push my function, or when I call my function, I pushed RIP. Now RBP gets here, and then right? So RSP is pointing there, RBP is pointing there as well. We'll just use this to indicate that this is where the pointers are pointing. Then we can do something like put pop, or not pop, can't pop yet. So we know that argument 7 right here is 1, 2 blocks away, right? So 16 addresses away is argument 7 in memory. So we can say move, say, we already used these registers. Maybe we can use. We only need to push RBP if we're going to use stack dynamic locals. No, you would do this. So this the SEC says use this convention when using stack dynamic locals. So that's the else. And or stack based arguments. So in this case, we have stack based arguments, right? arg8, arg7. So we need to address that, right? So using this method, because we need we need a base pointer to reach these arguments on the stack. Because let's say if you invoked this another function, right? So maybe you did a call function 1 again here, right? Then your stack would look a lot different, and then you need to know where the old RBP and stuff are. So once it pops back into place, the stack, you can resume with this base pointer, and it should be no problem. Maybe we'll look into that more in a different example. Okay, so move. Let's say I want to use a reserve register, so maybe I will also push RBX here. So say reserve register. So move RBX. The quad keyword of the address RBP minus or plus 16. Right? Since I want to go higher on the stack. And here, say that's this is our BX, right? So RBX gets added onto the stack. Okay, and then we sub RBX, sub RAX with RBX, and then same thing, right? Move RBX keyword RBP plus 24. This will access the second argument on the stack. So this is the arg7. This is the arg8. Subtract arg8. And then our value is fine, so we can return it back as RAX. But we need to finish up the standard calling convention, right? So remember here, this is what our current stack looks like, right? So we need to basically restore it back to pointing at RIP. So first we do a pop RBX, right? So now we have, let's opt it, this, pop RBP, okay? So now we have this. Okay, now we're at RIP, and RIP will be popped here. So now we're back at here, right? So notice when I'm back here, I'll use this right over here, right? So this is where we're at right now. Notice how my RSP is here. So I need to basically move it back to here, right? So I have to add RSP16. So even though the contents are still there, my RSP is now pointing to the previous part of the stack before my function call. And if you pushed anything onto the stack, you'll just override these memory addresses, which is fine. But that's how you would follow standard calling convention for functions. Yeah, so hopefully that helps you with writing functions. If you wanted to use stack dynamic locals, you would do that too. So maybe we can SDL. So let's say I wanted to use 8 bytes, right? We can move RSP by 8, or not move, add RSP 8. And then I would have 8 bytes of SDL right here. 8 SDL. Oh, and then here I would have to, before popping RBP, so here's the SDL, I would need to oh wait, it should be subtract 8, not net 8, so sub 8, so moving down, it should be add RSP. This will down. That's if you wanted to use SDLs. Right, so any questions on functions? If you're asking algorithmically, how do I set up a function? It just depends on what the function needs to do, right? So, for example, in this in the homework, right? I already told you that this function needs to convert the array of ASCII into an integer. So, and it gave you what variables you have to work with and what it needs to do. And you just have to write code. We would have to make an algorithm to do this. Return the corresponding value. If it does return, this one doesn't return, but you will need to print from this function. But all the tools you have are necessarily here. So once you figure out what to print and how much to print, it should be fine. But developing an algorithm is a completely different subject than how to write a function. Okay. Possible to give a quick example on how to read integers from a text file, a coding example. So what you're saying is you want me to code this loop for you. let's see. So remember our sysread. So I won't give you all the code, but I have something like set up for sys. Oh well, first you have to do a sysopen, right? So like open the file to read, right? And then once it's open, remember sysopen gives you a Rx is equal to the file descriptor, right? So it might be useful to declare the file descriptor. So maybe you'll say fd u since it started Rx fd or the set to 0. So and then we can say maybe you can store fd, right? So now that you have your file open, you can do a sysread, right? Sysread, passing in your fd. So it tells you how, and then you tell it how much to read. So what you'll do is probably the algorithm is read one character at a time until LF is found. Okay. And then store into buffer one character at a time. Okay. So that's your sysread incrementing by 1, and then now you have your buffer, right? So this ASCII buffer, right, contains the characters. So maybe, for example, you have 12, right? So you have 1, 2, like that, right? Stored in your buffer. So this is like ASCII buffer has this contents, right? Something like that. Okay. And then you just invoke this command, right? Move RDI ASCII buffer, right? Which is the address of the buffer, and then you can call ASCII to int. And then you would have to code how to take each one of these and turn it into the integer. Right, so not too bad, right? This one I think is very similar to assignment 4. Will you need an unassigned array to store the integer values? You can store the integer values in a variable called not give you the variable chair size, yeah. So you can store it into chair size if you want. Don't have to store in an array because your array will just be size of 1, right? Because there's only one integer. Right. So in this case, each one of these characters takes up a whole byte, right? But the integer itself, right? If you had int buffer, right? Int buffer basically can store the value of if we do it in binary, right? 1 1 1 1 1 1 1. So that is what is that? 256, right? Or 255, right? 0 to 255 for unsigned. So your integers, right? You can store the value 0 to 255, which should be more than enough for your text file, because your text file, I think, was, yeah, very small numbers. Are you writing C? No, I'm not writing C. This is just pseudocode. It's just a framework for your algorithm. This is assembly. But the stuff in green are just frameworks for an algorithm. Okay, so hopefully that helps you get started with your assignment 5. I don't think it's too different from assignment 4, just basically the inverse, and you're reading from a file instead. Today's going to be a long day. It's okay. I mean, I plan to give you Thursday off to study for your test and do your assignment, so it shouldn't be too bad. Good practice with functions as well, which is the bulk of this week's lectures. What are the main subjects that will be covered on test 2? So everything from functions all the way to tomorrow's lecture. So let's go recap what we did. We did functions, we did system calls, so we learned how to read and write. We did a lot of standard call and convention stuff. We did floating point values. We did we talked more about the tool chain. We did what did we do? Let's go ahead and look at the syllabus. So basically, can I highlight on this? Okay, so basically everything from this all the way to this and this. Everything more, oh god. Some stuff. But yeah, basically everything from week 2 all the way to week 4 is what we're going to cover. So a lot of it was functions and stack stuff on functions, and then the new stuff this week, which was opening files. These lighter topics are more conceptual than coding, which you need to kind of know how they work. So they're kind of important. Okay. So all that's going to be on your test. Make sure if you can do homework 4 and homework 5, I don't think you'll have much trouble with the exam for the coding parts at least, and then make sure you understand the concepts that we go over in class. But other than that, that is pretty much it. Shouldn't be too bad. This assignment has a lot nicer numbers, and you've already done the hard parts. It's just reverse engineering it now. And then you just add two new things, which is just the file open and the sysread. Will it be more conceptual stuff such as multiple choice or coding stuff for the test? So see, as a grader, I love multiple choice because they're so easy to grade. But they do not necessarily test the individual more than a written response question would. So I want to. My laziness tells me to make multiple choice questions, but the good instructor in me tells me that I should utilize more written response and grade an extra 12 hours. So I'll put in some multiple choice. No, no, I'll put in some multiple choice, but not a lot. It'll be roughly maybe the same amount as last test. So expect to see a similar structure to the last test. True or false is the real test of skill. That is true because it's a 50-50. But yeah, so test, I don't think the test will be that hard if you understand all the concepts. The coding portion isn't going to be as crazy as your homework assignment. It'll more likely look something a little bit more harder than, say, homework 4A. I think it was 4A. Let's see. I still have to grade your quiz and your homework. What was 4A? So 4a, remember when we looked at it, it was relatively simple, right? Make sure you do the process to call, and then make sure you do a similar function. So this one asks for the mean, and I did the one that does the difference earlier today. So they're relatively simple, not too bad. But it will most likely ask you to use stack-based arguments, or maybe initialize some SDLs or something. But it won't be like a convert this, print this thing. Okay, so hopefully that is not too bad. If you don't have any more questions, then the recording here.